So welcome to this third EuroTech talk. My name is Anita. I'm in charge of communications at the EuroTech Universities Alliance, and I'm hosting this EuroTech talk today. I would like to welcome very warmly our two speakers of today, which are Professor Pedro Reis of EPFL in Switzerland, where he heads the Flexible Structures Laboratory, and Professor Konstantinos of a joint unit of CNRS and Ecole Polytechnique in France. He works for the Solid Mechanics Lab there, and both have kindly agreed to give this talk today. So I work, as said, for the EuroTech Universities Alliance, and for those of you who are not familiar with this alliance yet, we are a strategic partnership of 6 universities of science and technology in Europe and in Israel. And besides EPFL and Ecole Polytechnique, we have on board the Technical University in Denmark, the Eindhoven University of Science and Technology in the Netherlands, the Technical University in Munich, and the Technion Israel Institute of Technology in Haifa in Israel. So together, we do a lot of nice things, and one of them, and well, one of our main purposes actually, is to encourage and facilitate collaboration between our researchers. Why do we do this? Because we think it's better to work together, and this is exactly what Pedro and Kostas are doing. So this is why we invited them to give a joint lecture today. And the topic they've chosen is Magneto-active soft materials and structures. Just a last housekeeping rule before we actually kick off. So today's session will be recorded and published afterwards. And we are very happy to have your questions. We will answer them at the end of this talk. So there will be time at the end where you can ask your questions. In order to ask your questions, please either type them in the chat or raise your little virtual hand and then speak up when you're asked to do so, and turn on your mic and camera then. So I think that's everything from my side. So yeah, Pedro, floor is yours.
Sure, thanks so much, Anita, and good morning, everyone. Thanks for coming to this talk by Kostas and myself. And so we're very happy to share some of our recent work, which is actually not the result of collaboration yet, but we've had many conversations, and we have over the time realized how much complementarity there was in what we're doing together. And so we were telling about magneto-active soft materials and structures, in other words, smart structures, and maybe the octopus is probably the ultimate example of a smart structure, given how reconfigurable and how compliant it can be. The reason for actually wanting to show you the octopus is actually to say that we do have multiple things in common. So Kostas and I, we like grilled octopus very much. I guess our connection to the Mediterranean is a source of that. Well, more recently, I've actually been learning quite a bit about octopus farming, and I realized that is not such a good thing. So I'm moderating my consumption of octopus these days. But now getting really into the business of today, we would like to first introduce ourselves, and then for the remainder of the talk, we'll be alternating and superposing our talking. And so I had the Flex Lab, the Flexible Structures Laboratory at EPFL, and we mostly dedicated to the study of the mechanics of slender structures. So this perspective of looking at buckling as something that is desirable for function, as opposed to the more standard view in engineering of buckliphobia, which tries to avoid buckling. And so in that sense, we care about mechanical instabilities and function that might derive in the post-buckling regime. And the big focus of our research toolbox is on these PDEs, not the mathematical ones, but precision desktop experiments. And I'll be showing you some examples later on. We're interested in many other topics than the ones we'll be covering today, so mechanics of rods, plates, and shells. But I'll leave some of those for a future occasion. And so passing it on to Kostas.
Hi from my side too. So I would like just to give my acknowledgements to the people. So the work that we're going to see today, it has been a work that has been done by a number of people working with me the last years. Deepayan and Matthias, they would be mostly their work that they're going to see today, but there are a number of results from Erato and Charlie, who were students that now they're continuing on different paths. And Zara and Zekwe are two students that are currently with me working on these subjects. And of course, the entire work started in LMS in 2010 with me and Nikon coming at the same time. And a couple of years later, Laurence, we formed a faculty group allowing to study this kind of soft magnetic materials. So having said that, so this is more or less the people involved of what I'm going to show. So the outline of the talk. Go next. So what we're going to discuss today is, first of all, what we call MREs is magnetorheological elastomers. That's what it stands for. And we're going to talk about fabrication, experiments, modeling, rational design of structures. So then we're going to move to the continuing modeling. I'll try to be brief. I'm not going to give a lot of details for the interest of time. Then Pedro is going to pick up to show very beautiful experiments on slender structures and theory that allows to model those. And we're going to try to close with some recent examples. We're going to go fast on that, what these materials can be used for.
Okay, so what are MREs? So MREs standing for magnetorheological elastomers. They're essentially composites that comprise a mixture of rigid particle inclusions that can be magnetized. They're not necessarily magnetic early on, that are embedded in a polymer matrix. And the particles themselves, and Kostas will actually tell you quite a bit more about these BH curves later on, they can be magnetized, and according to the shape of these curves, they can be these materials can be classified as hard magnetic or soft magnetic, with very different mechanical responses as a result, especially in the under the loading of a magnetic field. And of course, they have several advantages that have led to a lot of research over the past few years to emerge in the mechanics community. So they offer remote fast actuation, reversible shape shifting, and potentially even programmable magnetization. So it's a very rich design space to play with, and there's been lots of very exciting recent examples recently in the realm of soft flexible robots that can jump, that can swim. These materials can also be 3D printed, so customizable geometries, and so really very rich. Also in the biomedical field, there's been several groups looking at, for example, the reorientation of catheters during clinical operations where the tip is made out of an MRE material, and then the application of a magnetic field outside of the body that is being operated offers a function that existing clinical devices don't really offer. There, of course, when we have a new route for design of kind of structures, one wants to do predictive design. So one wants to have models that can guide us through the design process, and they can help us uncover all the interesting behavior that they can exhibit. And there's been some attempts and successful attempts in the literature, for example, for the deformation of MRE beams, work coming out from the group of Sean Rezau at MIT, Sean Chester at NJIT, and Pradeep Sharma at University of Houston, as well as by Ciambella et al. In Italy, who've done some very nice pioneering work on structural theories, but mostly beam theories and elastica theories, to predict the deformation of elastomagnetic beams. Kostas?
Yes. So let's try to dive in a little bit to understand some of the differences of these materials. So as Pedro said, these materials are composite materials. They're made out of a matrix, which is mostly polymer. Any polymer or a large variety of polymers can be used as a matrix phase. And then we have the option to use different particles. So if one uses particles that they can be magnetized, but after retrieval of the magnetic field, they are not magnetic anymore, like iron, then what we have is we have this curve below, this standard magnetization curve under the application of the field H. And we see that after cyclic loads, there is no hysteresis. So once we retrieve the magnetic field, the material is not magnetic anymore. However, these materials, they respond to magnetic fields. We're going to call those soft magnets. So if somebody is in the mechanics, then we can do an analogy with a nonlinear elasticity. So it's like we have nonlinear elastic materials. Now, instead of using iron type particles, one can use what we call hard magnets, like neodymium, iron, bore, cobalt, and a number of other materials. And those materials are magnetized permanently if we put them under a very strong magnetic field. So in that case, you see the curve below, where you see that after magnetization, removal, and coming back, we're left with a permanent magnet. The analogy with the mechanics, it could be done as having a material that is elastoplastic, meaning that after removal of the loading, there is a permanent deformation. The same in magnetism, after removal of the loading, we have a permanent magnetization. So going next, there is just a slide that it puts a sketch. So in the Soft-MREs, we have this composite material. We apply, suppose we apply loading, B up along a given direction. There will be magnetization as long as the load is on. When we unload, then the material comes back to where it was, is not magnetic anymore. If we go to the hard-MREs, which we're going to call HMREs, when we apply the load, there is magnetization. However, when we take the field out, then we have what we call a permanent magnetization. Now, our talk today is going to focus mostly on the hard-MREs. However, there has been a lot of work that has been done in LMS the last 10 years, also on Soft-MREs. I'm going to show you only a couple of slides just to give you a flavor of that. So going next about fabrication, this is mostly work together with Laurence Bourdelot. So the first type of fabrication is a classical fabrication of composite material. You pre-treat, one pre-treats the particle, we weigh the particles, we mix them with the polymer, we degas, and we use a mold. The mold can be is a custom-made mold that heats up the polymer, and then this mold can be put inside a uniform magnetic field next, so that you can have also microstructures. So if this mold is just left outside, then we have isotropic materials. If it is inside the magnetic field, then we can get what we call particle chains. So these are microstructures we have studied. And more recently, just a few months ago, with Laurence, was a paper published about using now 3D printing, custom-made, to print these kind of materials in more complex and more desirable shapes. Now, how do these materials behave? So we go to the next slide. We did a number of experiments. These are older setups that they were in Michigan by Nick Chontafilidis in a study that we collaborated together. So the way that these materials behave, and this is the way you should see them, is that by having the particles sitting inside, when we apply the field, there is a magnetization that builds up in this composite. And then on the right side, what we have is what we call magnetostriction. We're going to use this word a lot. Magnetostriction means the deformation of the composite, not of locally, but of the composite that deforms under the application magnetic field. The way that we have shown that this works is by reorganization of the particles. So you can see the video on the bottom is by applying the magnetic field, the particles try to align with the magnetic field, and this motion of the particles carry the matrix with them. And then the whole thing is moving, and it is extending or compressing or shearing. So you can get pretty large deformations with that, because the particle itself, it does not deform a lot. It has its strain of 10 to the -6, but the particle reconfiguration, it can lead to strains that are 10, 20, 30%. That would depend on how soft the matrix is. So this is what I want to say about Soft-MREs. These things exist also in hard-MREs. So this is the way people should understand the deformation. And then I'll let Pedro go to the hard-MREs.
Yeah, so in hard-MREs, the fabrication procedure is not so different. We tend to use slightly different polymers than Costas, but ultimately silicon-based polymers for the matrix. And so the way we fabricate these things, we start with the base, we mix in the magnetizable hard particles, magnetizable, they're not magnetic yet. And that makes a nice suspension that we mix, we degas and do very similar things to what Costas was describing. And then we mix in the catalyst to the base that already has the magnetic particles and the suspension. and then we wait. And then in 20 minutes, we have a solid that is this composite, which we can then magnetize in a magnetizer. So we pulse it with a large magnetic field around 5 Tesla. And this is what I want to show you on the next video. So videos also speak for 1,000 pictures. And so the mold would be laser cut, designed in CAD and laser cut. And so I'm going to show you the various steps. So throw the CAD design into the laser cutter. You cut the parts, which eventually will be assembled. There you go. That's Arefe, Basi, one of the PhD students in our group, showing how it's done. Okay, so in less than a minute, you have your mold. This is a Mickey Mouse example, literally, as you'll see from the shape of what comes out, is really just to show you the various steps. Now we pick up the parts and we go to the chemistry lab to prepare the polymer mixture. You see that this video was taken a few months ago when everyone was still wearing masks around the lab. Now she's walking up to our chemistry room. Lights on, where she's preparing the mixture. So that's the Mickey Mouse mold that she's assembling now. Tack, tack, tack. I don't know how the frame rate is coming across in Zoom, but hopefully it's clear enough. Excuse the mess on the chemistry bench. We're now going to weight all the relevant proportions of particles to polymer, and of course that will change the magnetization properties, and we can tune those. So we're mixing the base with the particles, as I briefly mentioned earlier, and now we're adding the catalyst. We're going to put the mixture, which is still in the liquid state, in a mixer that both mixes, but as a result of centrifugal forces, also degasses the polymer. So all the bubbles go one side, and the liquid suspension goes to the other. This mixing process does not lead to clustering, so the mixture is very nice and homogeneous. So similar to what Kostas was saying, now we degas the system to get rid of additional bubbles. You see that the suspension is still very much in a liquid state. Now polymerization has started. Takes about 20 minutes for the system to turn into a solid. And now the big box, you see there, that's just the amplifier. This is the actual magnetizer. So just some Helmholtz-like coils that allow us to pulse just for a few seconds the sample with a high magnetic field. So we're talking about 5 to 6 Tesla. And now we have essentially a soft magnet that has remained a magnetization. So it's a fridge magnet, if you like, but highly deformable. And so now the question is, how does the coupling of the magnetic field and the elasticity dictate the behavior of these systems? Okay, we don't want to watch the video again. Okay, so this is a typical experiment, and I actually show you this experiment a bit later on. So we always have a system of Helmholtz coils to generate the magnetic field. We can generate constant fields, we can generate constant gradients. Then there might be a mechanical component. In this case, is a poker that is going to indent the magnetic beam. So this is the picture from the top into the coils, where you see the magnetic sample, and then we can image the system. This is the power supply to drive the Helmholtz coils to provide the current. And yeah, so other than having the coils available and the fabrication procedure, the experiments are actually rather straightforward. And so now Kostas is going to tell you about this dichotomy between what can be considered as a material and what can be considered a structure. Kostas.
So as you have seen during the fabrication process, we're dealing with a material and a structure. And I would like to make this kind of clear due to the soft nature of this material. So when we do a simple simulation of a structure, that a magnetoelastic structure in between two poles, we have shown pretty recently, actually it goes back to very old, to the 60s, but we didn't know exactly what was going on. But we have shown very recently that when you put this structure under magnetic field, you create very non-homogeneous, heterogeneous strain fields. So even though it looks a bit counterintuitive, if we apply magnetic field on a sphere, Initially, the magnetization can be rather uniform, at least that's what it was thought for a long time, and this is kind of true. But if the material is soft, then what you can get is you get very different strains inside the structure. So in the middle of the sphere, you get extensive strains. In the poles, you get compressive strains. The whole thing extends, but locally, you get very different strains at the material level. So one has to be very careful when analyzing an experiment, what is a material response and what is a structural response? Because fundamentally, we have very heterogeneous fields. So this is something that I want you to keep in your mind as we go, because now what I'm going to talk about is about how we can describe material response at a given point, how the material, how the matrix with the particles, it works. Once we do that, then we can go and solve a structural problem. Before going there, I would like to remind for those that are not aware of or they don't remember well, is the magnetic problem. So you all know that you have a B field, which is a divergence free. In this case of magnetostatics, we don't have electric fields, we neglect those. And then we have an H field, and this standard magnet that you see here, and you see how the lines are, and the curl of H is equal to 0. And what we can see here is that these fields exist inside the material, but also outside the material. So that's one of the fundamental difficulties of magnetism, is that the fields exist also in the surrounding air. Unlike mechanics, that strains and stresses are inside the material. Now, a lot of people know about magnetization. So what is magnetization? That has took us some time for us to realize, at least in our from the mechanics point of view, is magnetization exists inside the magnetic body. It does not exist in the air. Now, the way that magnetization has been defined in physics community the last 100 years is through the constitutive relation that you see below. So you see that the B is mu naught H plus M. However, and this is something extremely important, is these quantities are defined in what we call the current configuration. And this equation is a constitutive equation, which means that somebody could have defined magnetization differently. What is measurable from Maxwell is B and H. That's what we measure in the lab. We never measure the magnetization. Magnetization is a constitutive parameter that is defined through this relation. Now, what does this mean in mechanics? So we'll go to the next slide. When we are in soft materials, right, what we have is we have two configurations usually. We have the reference configuration, the undeformed one, and the current configuration. So the quantities that they go from the reference to the current configuration is the H, B, and sigma, the stress. And then you have the equivalent capital H, capital B, and capital S. So in mechanics, we're used to work for solid mechanics in the reference configuration with the capital quantities. Now, that's where we're going to see that there is a big issue with defining magnetization. Magnetization, as we defined it before, is in the current configuration, but it does not have a clear definition in the reference configuration. So throughout the theories that I'm going to show you in our work, we have worked mainly with H and B. However, we're going to show that it is possible to work with magnetization, and Pedro has done most of the modeling during the magnetization. However, somebody has to be careful on how this magnetization is defined in the reference configuration. So now we'll go to the next slide, and this maybe there are a couple of slides that are a bit heavy. I'm going to go to how do we approach the modeling. So the materials, as we've seen, they're dissipative. We're going to do a full modeling of MREs of hard-MREs, and the soft-MREs can be considered as a limiting case of the hard-MREs. So if we allow the dissipation to go to 0, we can get to soft-MREs. So I'm going to focus on hard-MREs and dissipative systems. So this is a classical closest Duhem inequality where you have the dissipative inequality. So S F dot, B H dot, and W dot is the energy rate. So then what we have to do is to define an energy where the energy is simply a function of C. C is just a form of F, F transpose F, H. And because of the dissipative state, we need to introduce an internal variable, which for the moment I'm going to call HR, from H remanent. So there is a variable that when we take the fields out and nothing is applied in the system has something sitting in there, and that's HR. Or if you like, I'm going to relate it to magnetization. So then once we have this energy, the derivative of that energy with respect to C is going to give us the pure Kirchhoff stress, and the minimization is going to give us the divergence of S and the linear and angular momentum. The derivative with respect to H is going to give us the B field. So here you see that the energy carries the coupling of the problem, because it depends both on the mechanical and the magnetic fields. And you're going to, of course, have the Maxwell equation, scale of H and divergence of B, by minimizing that. And next, we have to say something about the remnant HR. The derivative of the energy with respect to HR is going to give us a field that is BR. If somebody would like to connect that with mechanics, people are not aware of magnetism, HR can be seen as the plastic strain, and BR can be seen as the back stress, what we call the Bauschinger stress. So these are similar notions in magnetism. Then, by using the standard material framework, of Halfen and Son in 75, what we can do is we can connect the HR and the H dot R through this relation of the energy and the dissipation. And here we make appear the dissipation. So we need the dissipation potential that is general. It has to be a function of the rates H dot, C dot, and the R. Next. Okay, so the dissipation appears in, below. So in general, it's going to be like that. Now, about the internal variable, I'm going to stay a couple of minutes on that. Is HR is the internal variable, and it took us a long time to realize that this HR has to be defined in what we call the intermediate configuration. We have a reference configuration, the current configuration, and the HR has to be defined in the intermediate configuration. It means that it's stretch free, meaning that when we take a polymer and we pull and we stretch it, this HR does not change. Okay. Now, in order to make contact with a physical meaning, and then I give pass to Pedro slowly, is that this HR, when we take the field out, so we'll go next, we're going to see that the current HR, the small HR, and the big HR, they're related through the rotation tensor, which means that the amplitude of HR in the current configuration and the curly HR are equal. And then when we take completely out the field, one can show that these HRs, they're nothing else but the magnetization. So the small HR is the current magnetization, the big HR is the capital magnetization, or up to a sign. And then what we show with that is that the small m has to operate as Rm, where m, capital M is the reference magnetization, which means that magnetization is going to be changing in orientation, but not in amplitude. And that's something that really we're going to see with the experiments of Pedro that's very important. Now, in previous theories, it has been proposed that the current magnetization has to be connected with through F. Unfortunately, that is not the case for the MREs that we're studying here. And we're going to see that this kind of definition can lead to kind of inconsistencies with experiments. So going next, then I'm going to go very fast on that. Once we have these variables C and H and R, then we can define a number of invariants. Invariants are extremely important, that they maintain that our energy functions and dissipations are positive definite, and they are objective, and they do not give crazy things. And then the energy is going to be, the energy function is going to be of the form. So we'll go next. Maybe you can make everything appear. We're going to have a mechanical part in the energy, which is Psi-mech, and then a magnetic part in the energy, which is going to describe the magnetic hysteresis curves. And then we're going to have a coupling part, which is going to give this coupling response. And of course, a very important feature about the magnetics is that we need to have what we call a background energy that is sitting in the background in the air, so that because there are magnetic fields that are there even if the material is not magnetic. And finally, we're going to assume here, and we'll show that it's sufficient, that the dissipation is only a function of HR and nothing. So going to the next slide. So this is the general theory. I really don't have time. There are a number of papers that have been written, and you have the list on the right. These theories have been coded in Abacus and user elements, and they're available in the Zinode open source. And we're able to simulate 3D material, what we call material RVs. So you see some images on the top. Then these 3D material RVs, the average response we extract and we use to calibrate or to obtain an analytical explicit model. And you see the comparisons in the bottom curves. So what you see here is on the left a standard magnetization applied magnetic field plot, where the C corresponds to the volume fraction of the particles. So if you have 10%, 20 or 30%, we increase the magnetization state of the material. And of course, we also increase the dissipation. Then, because when we apply the field, the magnetic field, we don't only form a magnetization state, but the material also deforms. And you see it on the right part, where you see what we call the magnetostriction. These are stretches, so this is like a strain. And you see that because of the dissipative character of the magnetism, we also get dissipative magnetostriction curves. And you see that the numerical and the analytical model, they're in a perfect agreement. Now, this analytical model now, so this is at the material response, right? And we have done a lot of work on providing simple expressions for the material response that can be used to analyze, going next, to model a structural problem, like the one that Pedro has shown. So this is an example, and Pedro is going to talk more about you. Here we have a magnetorheological beam, where a field is applied perpendicular to the beam, and as you see that the beam is deflecting, trying to reorient with the beam. The blue that you see around is air. We need to model the air in order to resolve the magnetic fields in the air. That is not entirely necessary if you're interested for deflection of the beam, but it would be necessary if you're interested to know what are the magnetic fields surrounding the beam. So this is an example, a numerical example, and then by comparing with experiments, going to the next slide, and then I'll leave the hand to Pedro. These models that have been able to recover pretty well available experimental data from Zhao for different slenderness of beams. And I think now the literature has a large number of data that Pedro is going to talk to you about.
Right. So as usual in mechanics, and especially when we're trying to design structures and devices, we don't often have to go all the way to full 3D FEM in our design and structural theories of linear beams, elastic rod theories, plate theories, and shell theories. They can be extremely useful, right? And so in doing so, to arrive to these structural theories for elastomagnetic materials, let me just review what we typically do when the material is purely elastic. This is a technique known as dimensional reduction, where we go from 3D of the bulk solid to the appropriate geometry. So if it's a beam or elastic, we'll be talking about the center line. So we want to reduce the problem to the center line. If it's a plate, we want to reduce the geometry to the mid surface, and likewise for a shell with a natural curvature rest. Okay, so these dimensional reduction techniques work for systems that have a large separation of length scale, so very slender objects where there's at least one dimension in the problem that is much smaller than all others. So for example, for a rod, the dimensions of the cross section will be much smaller than the length scales associated with the arc length. For a plate or a shell, the thickness is going to be much smaller than any other length scale in the problem. Okay, so for these slender systems, what we do is we start with our three-dimensional elastic energy, and then we integrate over the appropriate cross-section to reduce the elastic energy to the center line for the case of a beam or a rod, or to the mid-surface, here with mid-surface coordinates U and V for the case of a plate or a shell. Yeah, I'm just writing it for a shell, but it would be similar for a plate. Not mathematically, but the principle of reducing to the mid-plane, mid-surface is quite similar. Okay, so as a result, we now have 1D or 2D energy functionals that can be either minimized and by invoking the principle of virtual work to arrive to equilibrium equations, or we can compute the configuration of the system by minimizing numerically the energy functional directly, which is going to be computationally less costly and more efficient than, of course, if we were doing the full 3D FEM problem. Okay, so for the elastomagnetic problem, we follow an identical approach, but instead of just having the elastic energy in the system and then going through the dimensional reduction and the variation of energy minimization, we have an additional magnetic potential that relates from this interaction between the external field and the magnetization of the material. Okay, And so we invoke the same dimensional reduction procedure. Actually, mathematically, it's not so different. So you're doing an integral over the cross section, and then we specialize to the appropriate geometry. And so we have built up on recent work from that was mentioned a few slides before to come up with a hard magnetic elastica. And so elastica being the case of a beam that can undergo large rotations for the case of a constant field or a constant gradient. These are all planar deformations. We've also derived equations for rods, so slender structures, rod-like structures, filament-like structures in 3 dimensions that can undergo 3-dimensional deformation, and these are known as the Kirchhoff Rod Framework. So the magnetic Kirchhoff Rod equations essentially are the Kirchhoff equations plus distributed loads and torques that arise from this interaction between elasticity and magnetism. Okay. So we've also done similar procedures for plates and shells. Now for plates and shells, it becomes more difficult to arrive to the actual equilibrium equation. So it's typically more comfortable and feasible to deal with the dimensionally reduced energy potential, magnetic potential directly. So remember, this is what comes out of the dimensional reduction of the magnetic potential here. And we come up with expressions that can then be minimized numerically to compute the configuration of the problem. So I'll just make a comment here, whereas these 3 theories, so there's a paper has come out from our group for each of these types of structures, we use the deformation gradient. So you are in the description of the magnetization. So of course, I was talking about this before. It was in the plate problem, especially as a configuration that I'll mention later on that involves stretching, that we realize that in these problems using F or R, so the deformation gradient or the rotation tensor is identical because there's very little stretching in all of the configurations that we had studied. In the plate problem, because we actually had this one configuration with significant stretching, that's what we realized that the 2 were not equivalent. Using F or R were not equivalent, and I'll be substantiated what I've just said in more detail. But there's something that we learned by studying plates that we hadn't learned from the other 3 configurations. Okay, so let me show you a typical experiment. So I already described it. In this case, I also want to tell you about being able to predict more interesting instabilities like snapping. And so this is a clamp beam, and just by the variation or changing the polarity of the magnetic field, we can snap this beam between its 2 equilibrium or stable states. And of course, then the point is, well, can we predict what sets the snapping conditions and the critical parameters to do so? And so this is the geometry of the problem. We essentially have a beam, we reduce the end-to-end shortening, so we buckle into a stable configuration, and then it can be snapped into the second stable configuration. We have to be careful how we magnetize these beams. So it turns out that this symmetric anti-parallel magnetization configuration is optimal to induce magnetization. There's an argument related to the driving torques that are causing us to go the energy barrier to go from a stable state to the other. And so these are, it's preferable if we have the magnetization oriented in that way. Okay, so we have implemented all of these in FEM, in particular to track these more complex loading paths. It's common to use the Reis method. So we can use the Reis method in FEM also for these elastomagnetic materials. We can track the equilibrium paths, and you see here for 2 different values of the end-to-end shortening. And in some cases, these equilibrium paths can become quite complicated. Of course, not all equilibrium states are observable because some are unstable or they have higher energy states. But with this Reis method for these elastomagnetic systems, we can track the full equilibrium path. Okay, so the behavior is really quite rich. We can then augment the problem even further. So now we have a magnetic field on this clamp beam that is bistable, and on top of that, we also apply an indentation mechanical load P. And the only message I want you to get from this point is that the colored lines are experiments at different levels of the magnitude of the external magnetic field, and we can predict. And so here is the point force that you measure as a function of the position of the midspan. Okay, so we really have no fitting parameters, so everything is measured independently from the experiments, and using this machinery that Kostas was telling you about, yeah, we can really predict. And these are still, let me highlight, these are still full 3D FEM precise. Okay, so maybe actually grabbing on this configuration of a bistable system with a magnetic loading, that's actually motivated now. Previously was for a beam, so now we're going to talk about the shell, to think about a new concept, and so we haven't fully realized it experimentally yet, but a new concept for a Braille reader. Okay, so let's take a series of words, and this is the equivalent Braille alphabet. And so actually, interestingly, here we can think of a magnetic shell that when it's pointing upwards, it means that we have a Braille dot that is visible under haptic feedback, and when it points downwards, it's invisible. And so maybe this is actually an interesting candidate for a programmable Braille reader that can be activated with external magnetic field. So the way we make these samples is, again, similar to what you saw in the beam. We have to be careful how we magnetize the samples. We then have some elastic annulus that we pre-stretch. We then glue the pre-stretched annulus to the magnetic plate. We let go, so naturally the plate is going to be under compressive stresses, so it buckles out of plane. So this is now our Braille dot. And so now we can think about three components. First of all, the geometry of the bump, and so that has to satisfy very strict codes for Braille. So there's specific dimensions, or the height of the bump, the diameter of the bump, for the Braille dot to be acceptable and readable. Okay, so then there's two phases. In addition to geometry, we have to consider writing. So by writing, we mean switching the dome from one state, the upward state, to the down state, and we do that with a magnetic field. And then also in Braille code, there's some guidelines for the maximum force that the bump has to sustain with the finger due to the touching of the finger, so that it doesn't get erased. And so we have taken these Braille code guidelines into account. And so we have constraints on geometry, what can be made. We have constraints on writing, what can be activated through magnetic fields. And we have constraints on reading due to this limitation in the design force. And so by using the toolbox that we have been describing, the problem was, well, what is this design space on which we can play? Okay, so then we can, all of this work is numerical at this stage. I mean, experimentally validated, but numerical. So here you have the maximum load force that the system can attain before the shell moves to another state as a function of the applied magnetic field. And in this case, for realistic experimental conditions, there's actually not a lot of design possibility in the viable red vision here. So what we decided to do was actually to use a pressure differential, so to depressurize on top of the magnetic field, to depressurize the shell, to bring it closer to criticality, to bring it closer to the onset of buckling. And you see, this way we can actually have now lots of design solutions here that would satisfy these guidelines for Braille code. So at the moment, this proposal is conceptual, I mean, through concrete numerics. But we think that there's quite a bit to do here in terms of functional devices, as explained here for this Braille reader. Okay. Since we were talking about shells, let me show you another interesting application of these materials for tuning the critical buckling conditions for a shell. So as I'm sure most of you are aware of, so shells are difficult to predict in terms of the onset of buckling because of their very strong sensitivity to imperfection. So if you depressurize a shell, eventually it buckles. The question is, when does it buckle? So you can measure when it buckles, so you depressurize it, and at some point the shell goes bang, it collapses, and this is the maximum pressure that it can sustain. So one might like to try to predict that. There's classic predictions for spherical shells due to Zole, but when you do experiments, if you define this quantity known the knockdown factor, which is the ratio between the maximum pressure that the shell can sustain divided by the classical prediction, you see that all experiments give you a number less than 1. So you always overpredict what a system actually does. And why? Well, the reason is imperfection. So a lot of us, several of us have been putting a lot of effort recently in trying to be able to actually predict these knockdown factors, given knowledge on the distribution of imperfections. And typically these knockdown factors are regarded as an intrinsic quantity. They are part of the structure, and as a result, the shell buckles lower than a load than it should. Okay, so we can fabricate shells with a known defect. We can go and measure its critical buckling conditions, and what we've shown is that by applying a magnetic field for an elastomagnetic shell, we can tune, for the same shell, we can tune the maximum pressure load that the shell can sustain. And so in a way, we can tune the knockdown factor, so no longer it's an intrinsic quantity, but it's a quantity that can be controlled externally. We can go and do different experiments for different types of imperfections. We have knockdown factors that we showed to be able to vary as a function of the applied magnetic field. We can go back to our dimensionally reduced shell theories that I was telling you earlier. These are the dotted line, the straight line. So not only we can now predict knockdown factors, but we can tune. We have control over when they go. And when you find a mechanism like this, I'm sure it's going to be useful for someone somewhere at some point. Okay, so kind of quickly running out of time. So let me just quickly go into a similar work that we've done for magnetic plates. Here I'm going to go into a little bit more detail. So as a reminder, the historic-based continuum models that date back to the 60s to Brown et al., as Costas mentioned, and have been revisited recently by Zhao et al. They involve these sum of the elastic energy and the magnetic potential. So the magnetic potential depends on this magnetization that Costas was telling you about. And the question now, what do we do for the magnetization, right? So recent work was taking a magnetization in the current configuration and the original configuration that were related by the deformation gradient. And another alternative, the one that Costas proposed, is that, well, stretching, because the particles are rigid, stretching shouldn't play a role. And so the relevant mapping here should be with the rotation and not with the deformation gradient. So it shouldn't depend on stretching. And so we have developed a plate theory where we do indeed take a rotation tensor-based framework. We do our dimensional reduction. You come up with dimensional reduced expressions for the magnetic potential, and then we go and study test cases. So there's 3 test cases that we have looked at. One, a simple plate that deforms under pure bending, clamped at one edge. Second case, a plate that is clamped at 3 edges, and we apply a magnetic field. And the third case for a plate that is both pressurized and loaded magnetically as well. So in this third case, we're going to have stretching that is not going to be negligible, where in these 2 cases is mostly just bending. Okay. First case, no surprise here, deflection of this plate in pure bending as a function of magnetic field. Here we're quantifying deflection in Y, rise in Z, experiments, this R-based 3D FEM model, the R-based plate theory, everything agrees, no surprise. Likewise for the second case, so plate clamped at 3 edges. The R-based plate model agrees with the R-based 3D FEM, which agrees with the F-based. So F, again, I insist here, is the deformation gradient. R is the rotation tensor. Everything just agrees. There's no difference between these 2 versions. Now, things become a bit more interesting for this pressurized case. And so now here, the Y-axis is the deflection of the plate at its center point as a function of pressure that we're applying in the chamber for different magnetic fields. Okay, so you're already seeing here that pressure stretching has an effect for different magnetic fields. And so now this is just plotting the same plot that I had before. So the experimental data, let's go through the comparison with theory, both 3D FEM and the plate theory in a bit more detail. Okay, so we're going to compare the 2 versions of the theory on how we write in the magnetization. So one we're going to call first F-base, so using the deformation gradient, and the other one we're going to call it the R-base, so using the rotation tensor. Well, when the zero field is the zero field, then we just have a plate theory, no surprise. Already here you see a problem. So with the F-based theory, full 3D FEM, green should match with green, red should match with red, and there's a strong mismatch between theory and FEM. Whereas when we go to the rotation tensor-based theory, the 3D full FEM and the plate theory show these beautiful agreement with the precision experiments. Right, so this indeed provides experimental evidence of what Kostas was telling you for the right way to express the magnetization relating the current configuration to the original configuration. Now, maybe just as a little twist, it took us a long time to figure this out, because for a long time, we were actually starting from the 3D bulk theory, doing the dimensional reduction, and getting an F-based plate model, which is the dashed line, which was actually in good agreement with experiments. It was only after many months of banging our heads against the wall that we realized that when we do plate theory, you invoke the Kirchhoff love assumptions that normals remain unstretched, right? So that's one of the standard assumptions in beam theory and plate theory. And when you do that, you're essentially killing stretching. And so you're turning an F-based theory into essentially an R-based theory. And believe me, it took us a while to figure this out. And so again, highlighting the value of really putting the comparison between theory, numerics, and experiments to really try to learn something. So Kostas, maybe you want to make a comment at this point?
Yes, so a comment that comes, I mean, we also took us time to understand that, because if you go next slide, we were doing 3D calculations of RBEs, and this kind of notion, it was not necessarily, it was there, but you have to post-process it, you have to look for it. So what you see here is you see 3 RBEs that are magnetized, and when we do, after magnetization, we do stretching, shearing, or pure shearing, you will see that we have realized that the magnetization doesn't change in amplitude. It only changes in direction. So that was the reason that when we went back to the original model, to our explicit model as well, we were forced to define this HR internal variable in the intermediate configuration and not in the Lagrangian reference configuration. So we were running also in a similar problem. And we really believe that this is a feature of incompressible MREs. And in case that the MREs become compressible, I think that's an open question. So we don't know if this R is going to stay as is. But there what we see is that numerical simulations, experiments, they can be, things exist in there, but it's not always easy to extract this information. And then you realize that 3 experiments were not enough, for example, or all these numerics were not enough. We had to do, Pedro had to do another experiment that introduces stretching in order to see this feature. So I think I'm gonna, with this I'm gonna stop. I'm gonna go to the next slide. And I'm gonna be, I mean, we're almost finished now, 1 more 2 minutes. What I would like to show is that these frameworks that we develop in our lab and Pedro in his lab, they're generic, they're general, and they allow for design and simulation of a number of different structures. On the left, you see Soft-MREs. You see devices that they contain coils and MRE membranes, and you see the FEA in good agreement with a very good agreement with experiments without any calibration, actually, in that case. Below, you see instabilities that appear in film substrate systems, so you can drive patterning, surface patterning, based on combining pre-compression and applied magnetic fields, similar to what Pedro was using with pressurizing and using magnetic fields. So actually, the idea of using mechanical magnetic fields is a kind of very interesting idea, and I think it's only being understood very recently. But there is a lot of option for design space. And there you see on the top right, you see Soft-MRE examples of in the group of Garcia Gonzalez in Spain, where you use MRE membranes to drive cell migration. So these materials are very soft, so you can drive them in different directions by repositioning the magnets and pulling in different directions. And below, what you see is what you can do is you can pre-magnetize the samples, beams, or anything else any way you want. I mean, it's a matter of practicality, but how do you do it? But what you see here is you can make things flap asymmetrically or unsymmetrically, meaning that you can drive soft robots in one direction or turn them, or you can do all this stuff. So these are numerical calculations, but I think in a group of CT in Germany, they're also trying to use them in actual micro robots.
Yeah, okay, and we're running out of time, so I want to finish with one very quickly, an example in this theme of programmable materials, programmable metamaterials, where we're inspired by hard drives, where individual units can be switched to a 0 or a 1. So we did that magnetically. So there's a complicated structural system here that involves some curved beams, a shell that is bistable. We talked about bistability earlier, and you see this darker component here that is an MRE. And so we can move by the application of magnetic field this part up or down, so we can snap the shell. And when sorry about this, right? And so when we snap the shell into a different state, the mechanical response is very different, because now these curved beams are coming in contact with this blocker. And you see here the mechanical response for this state is very different than from the previous one. And so we can start playing with geometry, with non-linearities, and have MREs that are a subcomponent of a more complicated system. And so this has motivated us to design these metamaterials that have a writing phase. And so here we are selecting whether a shell is in the on or off state for each of these units. And so we're programming the material. And then in this case, we program it with this pattern. So every other cell has a different state. And then we can mechanical test the ensemble for example, the stiffness. And last plot, what we showed is that by choosing different programming ratios, we can obtain very different mechanical responses on a specimen post-fabrication. So we fabricate the specimen, and then we can program the mechanical performance as wanted. And this is very similar to what is done for hard drive. So I think this is just the beginning. Lots of exciting devices and structures that will be developed. To wrap up, so MREs are these new class of compliant materials that whose potential is not fully unraveled. Response is complex. Maybe Kostas, you want to say a couple more final points?
Yes. So we realized, and I think this is a strong point, that the modeling is very important in getting qualitative, but also quantitative response, because that's what allows rational design of soft structures. And I think both me and Pedro agree that there is a lot of unexplored ground for these kind of soft materials. And you've seen only some recent applications come out, but this is really, I think, in the beginning. So I think from my side, I would like to thank Deepayan and Matthias and my students, that they did a lot of work, and us for all these years of collaboration and continuing. And I'd like to finish from my point.
Yes, and so I think also the various people who worked on the EPFL side, the names are there, so past PhD students and postdocs in the group. And I also would like to thank Nick Triantafilidis. So it was actually a PhD thesis defense where Kostas, of a student by Kostas and Nick. I went to Polytechnique. I, of course, studied the thesis there, and that's what really opened the door for me to become interested on these MRE structures. And so I also wanted to thank Nick. I don't know if he's in the audience, but thank you, Nick. So Anita, I think we're done, and we're happy to take any questions.
Perfect. Yeah, thank you so much also for taking the request to deliver a joint talk. So literally, I think that works amazingly well. And indeed, so the official time of the talk is already over, but both speakers have agreed to still stay online if you have any questions. So I would like to open the floor indeed to some questions if you have any. Please raise your hand or type it in the chat.
Yes, so yes, please go ahead.
Are you talking about me?
Yes, Pedro one.
Thank you very much. So I'm Quentin Perron from the Defrost team in Lille, in France, working on soft robotics. Thank you a lot, Pedro and Konstantinos, for this presentation. It was truly amazing. I had the opportunity to work on the continuum robotics, dealing with magnetic actuation and with buckling issues. And so it just talks to me directly, and very, very impressive work that you have here. Okay, I would have actually two questions, but I can begin with one. I was interested by the work you presented, Pedro, on the buckled beam that you can snap with the magnetic field, and you presented like this, antagonistic magnetization, which you described as being optimal. I was maybe I missed it, but I was wondering, like, did you have like a specific method to determine like the best magnetization that will allow to do that, or was it like more intuition? Or
so our specific method was trial and error.
Okay.
Different magnetizations, and we we realized that when they were anti-parallel in this way, the critical buckling loads to make the switch between the stable one stable state and the other was lowered significantly. And that's prior to us having the actual toolbox and numerical tools to make this happen. So I think what will be very interesting now is to do an inverse design problem where, given the tools that we have now, to try to see maybe there might even be other magnetization patterns that might be preferable. And then preferable for what? What is your objective function, right? So even that is debatable. Then there's some practical limitations of what magnetization patterns you can actually implement. So maybe here's just very briefly, the way we made this magnetization pattern is that you have a beam that you fold in half, you magnetize in the folded state, and then you open it up, and then, right? So more complicated patterns will require additional creativity. But so in short, to answer your question, what was the specific method? Well, the specific method was trial and error.
I mean, makes sense, right? It's not simple to to get there with like a fully like automated optimal design.
Well, now we have some of the numerical tools that would allow us to tackle the problem that way, but we didn't. And then once we fixed the magnetization pattern, then there was enough to do that. We haven't gone back to the inverse design problem yet.
And maybe a small comment is that these phenomena are highly nonlinear. So when we're using the word optimality for highly nonlinear phenomena, I don't think there is a match of tools existing to do a fully optimization of a nonlinear phenomena of this type. So this is in the post-backing state that you have to see if it works or not, if it snaps or not. So I'm not sure that maybe some now recently machine learning. So if we're, with example, with these models, you can do a large scale of simulations, and then by using machine learning, you can invert somehow and try to pinpoint which are the possible states that are working better than others. But in general, the standard optimization approach is very difficult in these nonlinear problems.
Makes sense. Thank you a lot. I had a second question, but I will leave the place.
We have a couple of questions in the chat, and then we'll come back to you if there's still time. So I think Manish Thakur is asking, I want to know your opinion on the effect of high temperature on the MRE and its modeling, high temperature. So any comments, Pedro, on high temperature? They're polymers, so high temperature is...
Yeah, well, they're polymers, but they're elastomers, right? So they have a pretty high, they can withstand pretty high temperatures. So probably the thing I would worry about first might be the magnetization as a function of temperature, right? I mean, the Curie temperature above which magnetic effect will be could be raised, randomized, and with all honesty, I'm not quite sure what that critical temperature would be for these magnetic particles. Yeah, so which one goes first? Is it the magnet or the elastomer?
Yes.
Yeah,
I think in terms of temperature, there's not a lot of studies that have been done, and maybe in connection with the next question, which is regarding the magnetostriction curve, there seems to be hysteresis for magnetostriction, but not magnetization. I think this question refers to slide 11. You can go, because for hard-MREs, there is hysteresis in both cases. And then I'll make a comment about also temperature, about the previous. So in this case, you see that magnetization has no hysteresis for Soft-MREs, but you see some hysteresis for the magnetostriction here. Those are experimental curves. Actually, this hysteresis now we know is coming from what we call a viscoelasticity of the polymer. So this viscoelasticity does not affect the magnetization. We have a paper recently with Matthias and Dipayan, where we show the magnetization is not really affected by the viscoelasticity. We don't know yet. With Daniel Garcia Gonzalez, there is a paper just accepted, so probably we should go and see there. But there is the viscoelasticity in polymers is a very important feature that we're still yet to analyze. So in this case, what you see is that there is a slight viscoelasticity effect, hysteresis effect in the main magnetostriction curves, and these are mechanical. This is mechanical dissipation coming from the viscoelasticity of the matrix. We don't have yet a full model for that, but we're working on that. If you go to the hard-MREs, then you see both hysteresis in both curves. So I don't know if I have responded to the question. So these are questions from the chat.
Wonderful. Is there more questions for the moment?
If there is time for a question, yeah, Pedro, yes. The results presented in the modeling of single magnetoelastic element are very impressive. What about modeling the interaction between two elastic bodies made out of hard-MRE? Can the existing models account already for this additional difficulties?
Yeah. So there's a well, maybe you want to talk, Kostas, about dipole-dipole interactions, and then I can say.
Yes, so between two elastic bodies, well, I mean, our framework is general. So if you go to our papers, we can model any interaction. And the interaction usually comes, if you have two bodies that are in a distance, it comes through the air. And that's why I insisted that in some problems, this air has to be modeled, because the two bodies, they talk to each other through the air. The framework that we have presented is a 3D framework that can deal with any structural problem. Of course, there are numerical difficulties, but we can address those. I think Pedro recently, they have done a different approach in their coil called MRE. Was very nice, but they had a similar issue. Maybe Pedro wants to.
Yeah. Well, so first of all, I'll mention the person. So we haven't done it. Tomohiko Sano, who was a postdoc, is now a professor at Reis University in Japan, and so he was the driver for these problems on magnetic Kirchhoff rods. So where is the slide? And I mean, out of time constraints, I didn't talk much about magnetic Kirchhoff rods, but you'll see what I'm trying to say. Okay, so you have a highly flexible helix, because this is an elastomer, and then you can activate with a magnetic field. And in the original version of the theory that we worked on, that Tomohiko led when he was in the group, we did not consider dipole-dipole interactions. And so this dipole here was completely decoupled from a dipole quite a bit of arc length later in the rod. But now, when you undergo large deformations, 2 points that are far enough in arc length, they could actually become close in space. And so you can have dipole-dipole interactions. And so he has added these interactions into the theory. And so he has a self-interacting magnetic Kirchhoff rod that you can see as you apply a magnetic field. If the rod is, if the spring, if you like, is currently, is initially compact, then to open it up, you have to go over that barrier of dipole-dipole interactions. And then when they're far enough apart, then actually there's no dipole-dipole interactions. That's the regime that we worked on. And then you go back, you might have an hysteresis loop where the spring compacts again. So yeah, it can be taken into account. It's not trivial. For the case of rods, Tomohiko, after he left our lab, he has worked on that problem, and he has a very nice paper on this. And so I'm sure you can find it out. If not, write to me, and I'll put you in contact with Tomohiko, and I'll send you the paper.
Yes, and then in general for the structures, if you go to slide, Pedro, if you go to slide 33, you know, if you see these examples, we have a similar issue, but there we do a full three-dimensional loading, where you know, in the first device on top, you have in the first device on the top left, you have iron core that is interacting with the magnetic membrane. And actually, that's how the membrane is being attracted, is through interactions. So in that, we model the air. And then when you go in the bottom, there is a paper that we showed that this interaction of the neighboring wrinkles, they stop the wrinkles and they create a new feature which we call crinkling. They create something like a stepping. And that's a magnetic feature that has been only observed in graphene structures. But now is also observed in magnetic structures. So if you don't have magnetic and you do this compression, then you get what we call creasing, and the two parts, they will flip, they will contact with each other. But if there is magnetic interaction, the magnetics are pushing the two sides, and they will keep it like that. So in the modeling part, in order to take this into account, they need to take into account this interaction. Otherwise, it's not going to work. In our case, this interaction was taken into account through air, but this idea of dipole interaction can also work numerically, and I think it's interesting to be explored, where nodes, they contact, but it's a highly non-local problem, so it depends on how far you're going to go and model it. You can make the calculation extremely heavy, so I don't know in these two cases, in a full three-dimensional structure, what is more efficient?
Yeah. So Daniel has a nice question for both of us, Kostas, on the role of viscoelasticity. And so from at least what pertains to our work, I'll start by saying that everything that we have done is static. These are not dynamic theories, and they only work for two field configurations. Either, I mean, they can be extended in future work, but we haven't done that, either for constant magnetic fields or constant gradient fields. Okay, so there's no dynamics in the problem. Now, that's what we haven't done. In terms of the experimental system, these elastomers, they're actually not very viscoelastic at all, at least for the rates that we care about. And so we haven't taken viscoelasticity into consideration. We haven't worried about it. Instead of viscoelasticity, fluid viscosity, and adding that to the problem, that's something that we're working on active right now. So actually, it's useful to have this slide from Kostas up. So on the bottom right, you have these simulations for effectively structures that could be used as swimmers. So when you put these structures in a viscous environment, then what is the coupling between elasticity, magnetism, and the fluid loading? That is an open question. And so precisely to come up with solutions for swimmers, for cilia, for devices in microchannels, we want to add viscosity of the fluid as a loading component. I don't know if for you, Kostas, if you've maybe.
So, I think it's thanks Daniel for the question. I think viscoelasticity is a kind of an open question in these systems. If the loads are not too fast, I think there is some old work that indicates that the critical point in instabilities is not going to change with viscoelasticity. But what is going to change is, of course, the cyclic response. So if the instability is being created, so Pedro, for example, in some of the videos, you see that there is a little bit of viscoelasticity because as he loads and comes back, there is a little bit of hysteresis. But the way that the instability starts is not really affected too much by viscoelasticity. However, if things become faster, I don't know.
Yeah. Okay. Maybe still on the topic.
I think it depends on the rates, and I think Daniel, I've been talking Daniel, but there are some features there that are related to how fast things are operating, and it could be that these instabilities are something that I don't know. And usually the theoretical aspects of the problem are very difficult to analyze with viscoelasticity. So most of the studies are being done without viscoelasticity taken into account, but it's an open problem, so we should look into it.
Kostas, just I was going to, sorry for having interrupted you, but I was going to say, still in this topic of time varying effects, maybe not viscous in nature, but something that you have worked on, and for us there has been much less of a problem, most likely just because of the chemistry between the particles and the polymer. The degradation of the interface between the particles and the matrix can have time varying effects, right? So if you go through multiple cycles, if you have debonding, the response can be different. And I don't know if you want to comment on that. For us, it hasn't been a problem because of the chemistry, but for you,
I think this could depend on whether locally you have large strains or not. So in the beams, usually the nice thing about the beams is locally the strains are not necessarily so big, except if you are in these pre-stretching cases, etc. But if your strains, if you get strains that are pretty important locally, then cyclic is going to lead to fatigue problems at the interface debonding. And once you debond, and Laurence has done some work before, is once you debond, you realize that the materials do not behave as originally designed. So as I said, this is for me, these are new problems. Nobody has really studied them, and I think there is a lot of open space for that.
Okay, thank you very much. So I was wondering, because actually there is one word, this is not MRE, this is crystal liquid elastomers, I think by Vicky from Johns Hopkins University, where basically you can see that at different application rates, just purely mechanics. So this strain rate, it's changing somehow, let's say the stiffness of the polymer itself, and it's completely changing the backlink response, etc. So this is, to be honest, something I've never tried here with the MREs, but I wonder if, I don't know if you can do it, Kostas, or even you, Pedro, like applying the magnetic ramp at different rates and see if all these patterns are changing or not. Because I guess I didn't get actually what you said, Costa. So do you think that the wrinkling patterns do not depend on the effective stiffness, let's say? I guess because I'm not sure if for the long term the equilibrium state is going to be the same, or at some point as you may find different wrinkling patterns, let's say instantaneously, then you have like kind of different equilibrium states in the end on your structure. So
yeah, yes, I think it's related to the mechanical properties. So if you do things extremely, if you reach some critical level that you're really stiffening the material, then things will change, right? So things will change. So the question is how fast you apply things and how stiffer you make it. What I wanted to probably, what is interesting to see is, but because stiffness is a bit weird, if you are controlling the strain, and what we've seen in these wrinkling properties is that they're not too much affected by viscoelasticity. Okay. Because we're controlling the strain, but the stress at which they're going to happen is going to be different. So I think it's very important to ask the question: what is the control? Do you control force or do you control the strain? If you control the force, then because the material is stiffening, and I think Vicky's experiments or these they're done with a kind of a force control. So then things will change, but I'm not sure that the strains are changing. Okay. So I think these are not very clear. I think there is an older study by Zigang, so on something, but he was looking at strains, at pre-stretches. So when it comes to stretches, then it appears that these points do not change a lot. But again, I think there's not too much of literature on instabilities and viscoelasticity. I think maybe one or two, there's almost nothing, at least to my knowledge. I don't know much about nonlinear viscoelasticity and instability. So it's a very, very open subject in mechanics itself, and then let alone the magnetics at the same time.
Thank you very much, and congrats again. Super nice presentation and talk.
So there was one more question in the chat from Zoltan. I'm not sure it has been addressed yet. Could you have a quick look and then maybe we can wrap up?
Insightful. I would like to ask whether you are aware of any other shape-giving method by which these materials can be processed. More so, do you think some of these materials can be processed with light-based 3D printing?
I'm not aware. So 3D printing, yes, that was this pioneering work from Schwarz's group a few years ago. In terms of stereolithography, so light-based 3D printing, I think the first thing that you'll be facing as a challenge is the density difference between these resins and the magnetic particles. So if they sediments, then it's very difficult to go and polymerize layer by layer. If you can do some sort of density matching, then I believe that's doable. But again, I think this density difference is not going to be straightforward, and I'm just not aware of people who might have done it.
Yeah, me neither. I think light is mostly going to be affecting probably the polymer, but not the particles. So I don't know at this level, but I'm not aware of that. So very nice. I mean, interesting question. Thanks for the question, but I don't think I have a response. Yes.
Thank you very much also for the presentation and the answer. I think it's better if I try to clarify my point a little bit. So that on one of the slides you showed a microscope image of the composite itself, and I noticed that the scale was around 50 micrometers. So I was exactly worried about the sedimentation in terms of light-based 3D printing. Yes, exactly that slide. So if it's on the micrometer scale, then I assume that it would sediment faster, and then the problem becomes more pronounced. But are you aware of any other structure, any other composite that may have nanoparticles in it? Can you achieve a large magnetic response, larger magnetization if you only apply nanoparticles, or do you need micrometer scale grains in it?
I think in these materials, sedimentation is actually what we don't see too much. The reason for that is once you mix them, and Pedro has shown that, then the polymer starts polymerizing pretty fast, and the polymer is extremely viscous, so it does not allow too much sedimentation. Once the polymer has been formed, is a solid, there's no sedimentation issue anymore. So that's what makes these materials very good counterparts to fluids. MR fluids is one of the biggest problem is sedimentation. Whereas MR solids, they don't have these features, so there's no sedimentation. If you look on the left, in the Soft-MREs, we are even smaller, and we're about 4 microns particles. They're 2 to 5, and still we don't observe any sedimentation. And the reason for that is because really the polymer is very viscous, and it starts polymerizing immediately. And if you put it also in a small heating, then it's really going to polymerize faster. The sedimentation is not an issue. And I think also Daniel, the previous person that asked the question, I think he's working a lot on that. So you can use, now he has something that you can pre-treat a little bit the polymer and then use it in the printer. And then this helps even better to have a very good printing quality. So we don't necessarily have a sedimentation problem. I think Pedro is similar in his. Sedimentation is not necessarily a problem.
Right, because as you said, Konstantinos, is a mix between both the density difference between the particles and the polymer, but also viscosity. So something is very viscous. Say, sure, you can sediment, but it will take a long time. And if that long time is longer than the polymerization time, then you don't care. Going smaller scale. So I know here, for example, at least in experiments, this is where some practicalities become important. You know, there's many things that had to come together to make it realizable at these scales. And so actually, I think a big part of the innovation over the past few years is to find exactly these particles and the providers and polymers just with the right curing time as viscosity, right? So there's lots of things that have come together that have kind of motivated a lot of this work. And so, for example, the particles, just buy them from a company, and that's it. You mix with the polymer and you're done. And then you can worry about other things on the modeling front, on the experimental front. Nano powders to be used instead of these particles. Maybe it's possible. We haven't looked into it also for very practical reasons. To do that, you need a different type of lab, right? So to deal with nanoparticles, you need a different kind of safety. And we don't have that available in our lab. I mean, there's neighboring labs where we could do that, but we haven't felt the need to go that way. Now, of course, if you say that, light-based 3D printing, that would be a really nice frontier because you could make very complex shapes that are not available through the casting techniques that we're using. That's a great motivation to go and look at what's out there. We haven't had that urge, that need, but that sounds like a exciting direction to try things out.
Thank you very much for the help and for the answers.
Indeed. Thank you also from my side. So I suggest we wrap up here. Yes. Thanks again, Kostas and Pedro, for the very nice presentation and also for doing some overtime here. And thank you, of course, to all who participated. The talk will be on YouTube probably somewhere this afternoon in case you want to rewatch it. So thank you again. And see you hopefully soon.
Organizing that.
Thanks, Anita. Thanks to the Eurotech University Alliances for bringing us together.
Very welcome. Yeah. Bye-bye. Have a nice day.
Thanks for the audience. Bye.